Section: Introduction. In this section, we discuss how the recent surge in the use of large language models, LLMs, has revolutionized the field of natural language generation, NLG. These models have been instrumental in powering a wide array of applications, from translating languages to completing code and even supporting general-purpose chatbots. Their effectiveness largely depends on factors such as the amount of computing power available, the size of the dataset they're trained on, and the number of parameters they contain. It's been observed that their capabilities significantly expand as they grow in size. This has led to a trend where larger models are becoming increasingly popular, whether they are structured to only decode or both encode and decode information. However, as we push for larger models, we're also facing new challenges. Deploying these LLMs, especially considering the limitations in computing power and the need for quick responses on devices with limited capabilities, is becoming more difficult. This difficulty not only increases the cost for those providing these services but also for the end users. Specifically, LLMs in NLG work in two main steps. First, they encode a user's prompt, for example, translating "I love you" into German, and then they decode or generate the response, "Ich liebe dich." While encoding can often be done quickly and in parallel, decoding is a different story. It's done sequentially, meaning the model has to process each piece of the response one step at a time, which can slow things down significantly as the response gets longer. In light of these challenges, there's been a lot of interest in research aimed at reducing the time and cost of generating responses with LLMs. Traditional methods like model compression and parallel decoding are still being explored, but there's also a shift towards new strategies. These include combining models of different sizes to speed up decoding and using techniques like speculative decoding or creating a cascade of LLMs. Despite these advancements, there's still a lot of potential in exploring how to make the most of the quick encoding phase to improve the slower decoding phase. We believe that understanding the prompt in detail is crucial for generating an appropriate response. However, the current method of sequentially predicting each next piece of the response might not always be the most efficient. To address this, we propose a new approach that uses a hybrid model to make decoding faster. We use a large model to understand the prompt thoroughly in one go, and then a smaller, more efficient model takes over to generate the response. This way, we can still quickly encode the prompt in parallel, and the overall process doesn't take much longer than if we were using the small model alone. This is especially useful for tasks like translating longer texts. Our main contributions are introducing a straightforward method where an LLM guides a smaller model in decoding, combining different types of models for this purpose, and only requiring minimal adjustments to the smaller model. We've tested our approach on various tasks and settings, showing that it can significantly speed up the process without sacrificing much in terms of quality. For instance, in translation and summarization tasks, our method has achieved speedups of over 4 and 3 times, respectively, with only a slight decrease in performance. In the related work section, we delve into the balance between model performance and cost, exploring different strategies for making LLMs more efficient. These include model compression techniques like pruning, quantization, and knowledge distillation, where a smaller model learns from a larger one. Our approach can be seen as a form of model compression, where we replace the part of the model responsible for generating responses with a smaller, faster one but keep the large model for encoding prompts. We also discuss parallel decoding, which tries to generate multiple parts of the response at once but comes with its own set of challenges. Our method sticks to the traditional sequential decoding but makes it faster by using a smaller model for this step. Section Summary. In this section, we explore the challenges associated with deploying large language models, LLMs, in natural language generation, NLG, tasks, particularly in terms of compute limitations and latency constraints on edge devices. We introduce a novel approach, LLM-to-SLM, where a large model conditions a smaller, more efficient model for autoregressive decoding, resulting in significant speedups in tasks like machine translation and summarization with only a minor drop in predictive performance. This method falls under the umbrella of model compression techniques, offering a promising solution to enhance the efficiency of LLMs while maintaining high performance levels. Section: Conditional Approaches. In this section, we discuss various approaches and how they relate to our work, focusing on the integration of large language models, LLMs, with smaller language models, SLMs, to enhance efficiency and performance in natural language generation, NLG, tasks. Starting with conditional approaches, we observe that in the realm of multimodal learning, the technique of conditioning one network on another is more commonly seen than in the language domain alone. For instance, there have been instances where a language model's behavior is influenced by visual features. This concept of conditioning is somewhat similar to our approach, where we freeze the LLM during the fine-tuning process, a technique also explored in the vision domain. Specifically, we see a trend where smaller transformer decoders are conditioned on the outputs of larger encoders. However, our strategy diverges by linking a smaller network to a larger one specifically for the purpose of NLG. Moving on to learned prompts, our method aligns with the concept of parameter-efficient fine-tuning, PEFT, which utilizes trainable prompts that can be either continuous or discrete. Similar to some existing methods, we prepend soft prompts to the input while keeping all other parameters static. This approach mirrors how we integrate the representation from the LLM into the SLM. Our experiments include both trainable and fixed SLMs, with the latter involving only the training of a projector. Unlike other prompting methods, our primary goal is to minimize the cost associated with inference. Regarding SLMs, the simplest path to efficiency is through the use of smaller models. It has been demonstrated that SLMs are capable of few-shot learning and can even surpass the performance of GPT-3 in certain benchmarks. Another strategy involves training language models with a limited vocabulary, as seen in projects like Tiny Stories, which crafts SLMs based on stories generated by LLMs using vocabulary understandable by a 4-year-old child. While these approaches show promise for the future, our focus is on a practical hybrid model that leverages the high performance of LLMs with the efficiency of SLMs for a broad range of NLG tasks. In the context of hybrids, our work is closely related to models that utilize both LLMs and SLMs, with the latter handling the majority of computational tasks. Some methods propose a cascade of language models, where less resource-intensive models are used initially. Others suggest reusing the representation from the LLM to enable a smaller model to predict the next token more efficiently. Our method is distinct in that the LLM is only invoked once, and the SLM is conditioned on its representation. This approach is complementary to other techniques such as quantization and pruning, and we demonstrate its compatibility with speculative decoding methods. The core idea behind LLM-to-SLM is addressing the capacity limitations of SLMs by leveraging the high-quality representation from an LLM. This representation guides the SLM in predicting the next token in a sequence, which is crucial for generating appropriate responses. Our method facilitates the connection of an LLM encoder to both encoder-decoder and decoder-only SLMs, regardless of their model family. This strategy compensates for the lower parameter count in SLMs by conditioning their predictions on the LLM's representation of the prompt, leading to faster generation times since only the SLM is involved in autoregressive decoding. In terms of fast autoregressive decoding, when given a prompt, traditional methods require multiple forward passes through the LLM decoder, which is computationally expensive and cannot be parallelized. Our proposal shifts the burden of autoregressive decoding to a smaller model, significantly reducing the runtime as the number of autoregressive steps increases, ultimately aligning it more closely with the original runtime of the SLM. This approach not only preserves the encoder's capacity but also enhances efficiency in generating responses. Section Summary. In this section, we introduce a method called LLM-to-SLM that addresses the low-capacity issue in SLM by leveraging high-quality LLM representations to guide next token predictions in the SLM. By connecting an LLM encoder to both encoder-decoder and decoder-only SLMs, we compensate for the smaller parameter count of the SLM, leading to faster autoregressive decoding as only the SLM is involved in generating output tokens. This approach aims to combine the strengths of different network sizes for efficient NLG tasks, enhancing performance by conditioning SLM predictions on superior LLM representations. Section: Architecture. In this section, we discuss the architecture of our system, which includes a large language model, LLM, encoder, a projector, and a smaller language model, SLM. Starting with the LLM encoder, we designed it to take a prompt of a certain length as input and transform it into a high-quality representation. This process is computationally intensive, so to make it more efficient, we decided not to update the LLM's parameters during the fine-tuning phase. Instead, we pre-compute the representations of prompts, which allows us to train the LLM-to-SLM conversion on a smaller budget. We achieve good representation quality by using large pre-trained models that include both an encoder and a decoder, but we only use the encoder part. The reason for this is that the last layer of the encoder provides a clear and direct way to encode prompts for the SLM, unlike in decoder-only models where it's harder to identify which layer best encodes the prompt. Next, we introduce the projector, whose job is to align the representations between the LLM and SLM. It takes the high-dimensional features from the LLM and converts them into a lower-dimensional form that can be easily integrated with the SLM's embeddings. We found that a simple yet efficient design for the projector is a small multi-layer perceptron, MLP, that includes a linear transformation followed by a ReLU activation and another linear transformation. Moving on to the SLM, it takes both the tokenized input and the projected representation from the LLM, and maps them to a response of a certain length. During training, we also include the target sequence in the input to predict the next token through a method known as teacher forcing. For inference, we append the predicted tokens instead. We use pre-trained networks for the SLMs but fine-tune them to handle the high-capacity encodings from the LLM. Additionally, we experiment with learning from both the actual data and sequences generated by the LLM. A key aspect of our framework is how we integrate features from the LLM into the SLM. We prefer to do this early on, which allows us to treat the SLM's internal structure as a black box. This approach works well with both encoder-decoder and decoder-only SLMs. Initially, we embed the tokenized input using a trainable matrix. To fuse the features, one straightforward method is to replace the SLM's prompt embedding with the projected LLM representation. Another method, which we used in our main experiments, is to add the projected LLM representation to the SLM's prompt embedding. This preserves the relationship between the embeddings of the prompt and the target or predicted sequence, while also using the LLM representation to adjust the prompt embedding. When adding the LLM representation to the SLM's prompt embedding, we need to ensure the sequence lengths are aligned. This can be challenging when combining models that use different tokenizers and vocabularies. Our solution is to use the LLM's tokenizer and embedding matrix for both models, which simplifies the process. We also introduce two new linear layers to facilitate this, one that projects the LLM embeddings to the SLM's embedding space, and another that adapts the SLM's output to match the LLM's vocabulary. While there are other methods for integrating features from different models, such as cross-attention or feature-wise linear modulation, film, layers, we chose to add them because it's simple and requires minimal modifications to the SLM. Section Summary. In this section, we introduce an architecture that aligns representations between large language models, LLMs, and smaller language models, SLMs, efficiently. We freeze LLM parameters during fine-tuning to train LLM to SLM on a small budget by pre-computing prompt representations. By leveraging pre-trained encoder-decoder models and a projector to align LLM and SLM representations, we can integrate LLM features into SLM at an early stage, simplifying the process and ensuring effective feature fusion. Section: Experiments. In this section, we aim to shed light on how our newly introduced method, which we refer to as LLM to SLM, stacks up against using either large language models, LLMs, or small language models, SLMs, on their own. Our main focus is on comparing their performance and how quickly they can operate. To do this, we first put LLM-to-SLM to the test across 3 different tasks: translating languages, summarizing texts, and tuning instructions. After that, we delve into how computationally efficient our method is. Lastly, we conduct a thorough investigation through ablation studies to see how LLM-to-SLM performs with SLMs of different sizes, its relationship with speculative decoding, and how it measures up against PEFT, prompt engineering and fine-tuning, methods. For our experiments, we used a variety of pre-trained models, denoting the combinations of LLMs and SLMs as LLM-to-SLM. Specifically, we utilized T5 encoders as our LLMs and chose T5 encoder-decoder models and GPT-2 decoder-only models as our SLMs. It's worth noting that our LLMs have significantly more parameters, ranging from 8 to 55 times more than the SLMs. Since we keep the LLM unchanged in our approach, we selected high-performing LLMs that were pre-trained for the specific tasks we're examining. The choice of model varied depending on the task. For generating outputs, we used a technique called beam search for translation and summarization tasks, and another method known as nucleus sampling for instruction tuning. We evaluated our results using task-specific metrics: Sacre Bleu for translation, Rouge for summarization, and GPT-4 scores for instruction tuning. Additionally, we measured how long it takes to generate a single token in milliseconds, using a setup where we generate 100 tokens from a prompt of the same length, on high-end NVIDIA GPUs. When it came to training our models, we used a batch size of 128, optimized them using AtomW with specific settings, and followed a particular learning rate schedule. All of this was done using the Hugging Faces Transformers library, with more detailed training information available in the appendix. For the machine translation task, we translated English into German, French, and Romanian, using different datasets for each language pair. We employed T5 large as the LLM encoder and experimented with T5 small, T5 1.1 small, and GPT-2 as SLMs. The T5 small and GPT-2 models are significantly smaller than T5 large. We trained our models for a set number of iterations, except for T5 large, which was already pre-trained for translation and used in a zero-shot manner. Our method of using the LLM to generate training labels showed promising results, with our LLM to SLM variants nearly closing the performance gap with the LLM, and in some cases, significantly outperforming the SLM baseline. In the summarization task, we evaluated our method on the CNN Daily Mail dataset, again using T5 large as the LLM and GPT-2 as the SLM. Unlike with translation, we found that training directly from ground truth labels was more effective than distillation. Our LLM to SLM model not only matched but slightly exceeded the performance of T5 large, while also being 3 times faster. Remarkably, it achieved this with a much smaller decoder, showing that our method can offer significant improvements in efficiency without sacrificing quality. Section Summary. In this section, we compare the performance and runtime of our proposed LLM to SLM method with LLM and SLM separately across machine translation, summarization, and instruction tuning tasks. We use pre-trained T5 encoders as LLMs and T5 encoder-decoder and GPT-2 decoder-only models as SLMs, with LLMs having significantly more parameters than SLMs. Our method shows promising results, reducing performance gaps between LLMs and SLMs, such as achieving comparable BLEU scores in translation and slightly exceeding Rouge scores in summarization while offering speed improvements. Section: Instruction Tuning. In this section, we delve into the potential of our method within a challenging instruction tuning scenario. Unlike the traditional approach of fine-tuning, where training and evaluation are focused on a single task, instruction-following models are trained across a wide array of tasks. They are then evaluated based on their ability to solve new, unseen problems. For this purpose, we utilize Flan Alpaca XXL as our large language model, LLM, which is a version of the T5 model with 11 billion parameters. This model has been trained on FLAN, a collection of 1,800 tasks, as well as the Alpaca dataset, which includes 52,000 generated instruction following demonstrations. To assess the performance, we use the MT Bench dataset, comprising 80 tasks across 8 categories, with GPT-4 serving as the judge. As our smaller language model, SLM, we choose FLAN T5 base, a T5 model pre-trained only on FLAN data, and then fine-tune it using the Alpaca dataset. It's important to note that our LLM, FLAN Alpaca XXL, has 55 times more parameters than the FLAN T5 base. The results, as shown in the reference table, reveal that our LLM achieves an average score of 3.2, excelling particularly in writing, extraction, and roleplay tasks. In comparison, FLAN Alpaca base scores relatively lower at 57.5%, highlighting the significant role of scale. By fine-tuning FLAN T5 base on Alpaca data, we managed to increase its score to 62.3%. Further improvement is seen when employing our LLM-to-SLM method, which boosts the score to 73.4%, outperforming the SLM alone by more than 10 percentage points and closely competing with other models evaluated without any prior specific task training. Moreover, our LLM-to-SLM method demonstrates a superior balance between performance and runtime when compared to all other models, as indicated in the table. Qualitative examples in the appendix showcase that our LLM-to-SLM can generate fluent and sensible responses. Despite outperforming the SLM alone, our method does not reach the performance levels of the LLM. This is partly because, unlike tasks such as translation and summarization, the models are trained for general problem solving and evaluated on a diverse set of challenging tasks. The significantly smaller capacity of the SLM, despite hints from the LLM, may limit its ability to fully replicate the LLM's performance. Additionally, the initial performance gap between the SLM and LLM in instruction tuning is considerably larger than in our other experiments, suggesting that the SLM needs to be somewhat proficient in the task to fully benefit from the rich LLM prompt representation. However, as SLMs continue to evolve and improve, we expect our method to become increasingly effective in instruction tuning. We also explore the impact of different SLM capacities on predictive performance in an ablation study, highlighting that smaller SLMs can significantly benefit from our method. Regarding computational efficiency, we demonstrate that our method achieves significant speedups in tasks like machine translation, summarization, and instruction tuning, with minimal loss in performance. This efficiency gain is further illustrated through performance runtime trade-off curves. Our findings suggest that by adjusting the size of the LLM or SLM, we can achieve greater efficiency, with our LLM-to-SLM variants performing significantly better than the SLM alone, nearly matching its runtime. In exploring the use of tiny SLMs, we scale down the SLM and observe its impact on predictive performance and runtime. By reducing the number of layers in a pre-trained GPT-2 model, we create variants with significantly fewer parameters. These truncated SLMs, when used in our LLM-to-SLM method, outperform the SLM baselines by a wide margin while maintaining similar runtime. This demonstrates that our method's performance gain over the SLM alone is significantly greater when we reduce the size of the SLM, consistent with our instruction tuning results. Section Summary. In this section, we explore instruction tuning using a method that trains models on a variety of tasks for general problem solving. By fine-tuning a large language model, LLM, on instruction following tasks and then transferring knowledge to a smaller language model, SLM, we achieve significant performance improvements in writing, extraction, and roleplay tasks. Additionally, by scaling down the SLM, we observe that our method can maintain predictive performance while significantly improving computational efficiency, showcasing the potential for more effective instruction tuning as SLMs continue to evolve. Section: Speculative Decoding. In this section, we delve into the concept of speculative decoding. Through our empirical evaluations in the realms of translation and summarization, we've observed that our approach of transitioning from large language models, LLMs, to smaller language models, SLMs, can achieve performance levels comparable to those of the LLMs themselves. However, when it comes to instruction tuning, we've noticed that despite significant improvements, our LLM-to-SLM strategy might not fully reach the performance heights of the LLMs, as we've discussed in a previous section. Speculative decoding, on the other hand, offers a promising solution by ensuring that the output distribution matches that of the LLMs, although it requires multiple invocations of the LLM. Since our method and speculative decoding are complementary, we've combined them to achieve LLM-level performance while also gaining speed improvements. Specifically, we use our Flan Alpaca XXL to Flan T5 base as a draft model, applying the encoders of our LLM and SLM just once to encode the prompt. Then, we repeatedly call upon the decoder of our SLM for the autoregressive generation of draft sequences. The results show that we can match the LLM's performance with our LLM-to-SLM approach, and still be 1.5 times faster, compared to the 2.3 times speedup when using LLM-to-SLM alone. We've included additional speculative decoding results for the translation task in the appendix. Moving on to parameter-efficient fine-tuning, our method shares similarities with PEFT methods. For instance, soft prompt tuning involves adding learnable tokens to the prompt embedding. In contrast, we enhance the prompt embedding of the SLM by adding LLM representations in an element-wise manner, which can be seen as a type of conditional prompting. We've compared the performance of PEFT methods with our approach by keeping the SLM fixed and only training the projector. After adjusting the hyperparameters of the PEFT methods to match the total number of parameters of our projector, we found that our method surpasses all PEFT methods in both summarization and translation tasks. This suggests that conditioning on the LLM positively impacts performance compared to non-conditional approaches. We've also reported additional PEFT results for a more limited training regime in the appendix. Regarding the LLM versus SLM tokenizer, when we replace the SLM embeddings of the prompt with projected LLM representations, the SLM's tokenizer can still be used, even if its vocabulary differs from that of the LLM's tokenizer. In such cases, we can skip the additional embedding down projection and head layers. For instance, in transitioning from T5 large to GPT-2 for machine translation, we discovered that using the LLM's tokenizer yields better results by an average of 0.45 blue points across all languages, possibly because the T5 tokenizer also accommodates non-English languages. We also explored the effects of replacing SLM embeddings with versus adding them to the projected LLM representations as feature fusion strategies. The results for machine translation indicate that both addition and replacement strategies perform equally well. Lastly, in the context of translation, we found that using labels generated by the LLM for training can lead to an improvement of up to 1 blue point over using ground truth labels. However, this finding does not universally apply. For summarization, training with ground truth labels results in an average Rouge score that is 0.44 points higher than when using LLM-generated labels.